Let's go ahead and get started in Chapter 2. In Chapter 2, we begin to introduce techniques for solving specific types of differential equations. Since this is our first experience solving differential equations, it makes sense that we're going to try to deal with the simplest possible case in some sense. And Chapter 2 specifically focuses on first-order differential equations. So that tells us right away that in this chapter, in all of the differential equations, the highest derivative that will appear is a first derivative. To be more specific, in this first section, the particular type of differential equation that we'll focus on are first-order linear ODEs. Linear differential equations, as we define in section 1.1, have the property that all of the independent variable and derivative terms are linear. That is, they're all to the first power. We'll look at a few different types of first-order differential equations in other sections in this chapter, but in this section, in section 2.1, that is the precise type of differential equation that we'll be looking at, first-order linear. So that implies that there's a pretty specific structure to the differential equations that we'll be solving. I've kind of given a little picture here of what that structure must be. Since we know our differential equation in this section must be first order, I know that the highest derivative that will appear is a first derivative. In addition, since we also know that our differential equation must be linear, I know that if there is a y prime term and a y term, both of those terms must be to the first power. That suggests that any terms that act as coefficients on the y prime term and the y term must exclusively be in terms of the independent variable. I further assume that in this little picture, all of my y terms have been grouped into this second term. All of my y prime terms have been grouped into this first term. So any additional terms here would also be strictly in terms of the independent variable. We don't typically write differential equations with these squiggly boxes. And so instead, here's a more formal version of that general structure that we'll be dealing with. Here I've written the general first-order linear ordinary differential equation as y prime plus p of ty equals g of t. So the p of t and the g of t are written as functions, but I just think of them as general expressions that involve the independent variable t. So this p of t is just a placeholder for any general expression that is in terms of t only. And then the same is true for this other expression here on the right-hand side. Notice this has a slightly different structure than the one we just highlighted, but to get from this original structure with my wavy boxes to this more formal structure, I think you'd agree there would just be one or two simple steps of algebra. I would take this term here, move it over to the right, and then if there are terms in front of the y prime, I would divide through by those in order that my coefficient on y prime would be exactly positive 1. So any differential equation which has this structure could be reworked so that it could be written in this structure here. Further down the page, I provide some examples of first-order linear ODEs, and I note that these don't necessarily have our standard form right away, but I think you'd agree that there's just a couple simple steps of algebra which would allow us to manipulate these so that they would be into the standard form. For example, in this first differential equation, I have t sine of t times y prime. We just noted that this standard form requires the coefficient on y prime to be positive 1. So I could imagine taking this differential equation and as a first step just dividing the entire thing by t sine of t. And you should confirm that the same is true for the other examples that I've provided here. At the top of the second page, I have another quick note that it may be tempting to try to solve these by isolating y prime and then anti-differentiating. After all, y prime is a derivative. If our goal is to solve for y, then it would feel natural to isolate that y prime term and then undo the derivative. But as I indicate here, this approach will not work since when we isolate y prime, the expression for y prime will have y's in it, and we don't know what y is, so we can't integrate y. Therefore, just using that straightforward approach of trying to isolate y prime and then anti-differentiate will not work with this type of differential equation. The approach that we need to utilize is in fact more complex. And in order to demonstrate that approach, I want to start by looking at a couple specific examples, and then we'll look at how the approach works in general. So let's take a look at example 1. Again, the purpose of this example is to demonstrate the procedure that we'll use to solve first-order linear ODEs. In this particular example, I will not explain all of the details, but I just want to use this example to give an introduction to how the procedure will work. The differential equation we're asked to solve is y prime plus cos of ty equals cos of t. This differential equation is already in standard form. So I notice some function, some expression in terms of t's times y, and then on the right-hand side I have some other expression in terms of t's. Those, referencing the standard form stated above, are exactly the two ingredients p of t and g of t. So I like to go ahead and state those explicitly, just so that it's clear. It just so happens in this example that both p of t and g of t are cosine of t. It's kind of a coincidence, that won't happen very often. And then next we're told to multiply by a new function. So this function mu of t is given as e to the sine of t. And we're told simply to multiply my entire differential equation by that function and see what happens. So let's give it a shot. Just to clarify the steps, what we're being asked to do here, we're going to take our entire differential equation and we're going to multiply it by this mu of t. In particular, we've been told that mu of t equals e to the sine of t. So I'm going to take my entire differential equation and multiply by e to the sine of t. Let's go ahead and distribute that term all the way through to every term in my differential equation. Now, at this point, I will admit that it's not obvious what we're trying to look for, what sort of property we're trying to identify. But I'm going to focus on the left-hand side. Let me think about the structure of the left-hand side of this differential equation. We have e to the sine of t times y prime. That kind of feels like two separate functions, e to the sine of t, and then the derivative of y. And then our second term, which we're adding, is e to the sine of t times cosine of t times y. And if I choose to group these terms in a specific way, here I've grouped the e to the sine of t along with the e to the sine of t cosine of t. I'm sort of choosing to group those two functions together. And then similarly, I've got y prime and y, my unknown function y and its derivative. Again, this isn't totally obvious, but if you think about this left-hand side, you can kind of see that it has the structure of a product rule. Here, let's look at these ingredients. I've got e to the sine of t, that's kind of some function just by itself, multiplied by the derivative of the second function, plus the second function not differentiated, just y, and then this e to the sine of t cos of t is exactly the derivative of this quote-unquote first function. So this left-hand side, and again, this isn't obvious, so I recognize that you might not look at this and immediately say, or immediately be able to identify that that's what's going on, but this left-hand side is in fact an example of the product rule. Let me spell out what I mean by that. I claim that this left-hand side has the structure that it is the derivative with respect to t of e to the sine of t times y. If you don't believe me, try it. Evaluate this derivative. We have two functions. Again, here y is not just a variable. We're thinking of it as a function of t. So I have two separate functions. And if I was asked to take the derivative of those, since they're multiplied, I would apply the product rule, and I'd end up with exactly this expression on the left-hand side. My right-hand side hasn't changed at all. I'll just go ahead and rewrite that for reference. So if my goal is to isolate y, then I can actually get at y in this equation, in this form of the equations here, by doing the antiderivative with respect to t. That is, if I integrate this left-hand side with respect to t, that will cancel this derivative with respect to t, and that'll leave me with these two terms here. And then I believe I'll be able to isolate y, and that will give me my general solution. So I'm going to introduce an integral on both sides of this equation, and both of the integrals will be with respect to t. On the left-hand side, I expect that the integral with respect to t will simply cancel the derivative with respect to t. So on the left-hand side, I'll just be left with this inner function, this inner expression. So I'll have e to the sine of t times y. Now that's good because, again, my goal is to isolate y. My goal is to solve for y. And so whatever's happening on the right-hand side of this equation, I believe I should just be able to divide through by this function, and then that will give me my solution for y. I'll have an expression that says y equals, and then that will be the general solution of my differential equation. On the right-hand side, I now have an integral with respect to t, and this particular integral is actually set up perfect for u substitution. This integral is kind of unrelated to everything that we said previously about the left-hand side. I just happen to end up with an integral, and at this stage, I'm going to need to evaluate this integral. I'll use substitution, u substitution, to evaluate this integral. And the integral on the right-hand side evaluates to e to the sine of t plus a constant of integration due to the fact that this is an indefinite integral. So as I mentioned, my goal will now be to isolate y. And I can do that by simply dividing both sides by e to the sine of t. This yields the function y equals 1 plus c e to the negative sine of t, and this is the general solution of my differential equation. Let me just, before we move on and try this again, let me just recap what we just did in this example. We started with a first-order linear differential equation in standard form that enabled us to identify the ingredients p of t and g of t. And then we were provided with this sort of mysterious mu of t. To be honest, I don't know exactly how this mu of t, why this specific function was generated, but it just so happens that this function was perfect, because when I multiplied that function by my entire differential equation, the left side turned into, the left side had all of the correct ingredients so that it could be turned into or represented as a product rule. And then rewriting my left-hand side as that product rule enabled me to integrate both sides, which then enabled me to easily isolate the function, the variable y, which is the solution for my differential equation. Let's try that again with a second example. Let's take a look at example 2. Example 2, we're told to follow the same procedure as we did in the previous example, using the differential equation y prime plus 3 over ty equals t plus 1 over t, with a mu of t equal to t cubed. The first order linear differential equation we're given in this problem is already in standard form, so I can identify the key ingredients p of t and g of t. Here I have p of t as the coefficient on y, so that'll be 3 over t, and then g of t is the expression in terms of t on the right side of the equation in standard form. So in that case, that's t plus 1 over t. Now, as with the previous problem, my first step is going to be to multiply by this mu of t function. I'll reiterate that at this point, we haven't been told how to generate this mu of t. This mu of t is kind of a mystery, but we will develop that in subsequent examples. Multiplying the entire equation by t cubed and doing some simplification gives me this equation here. And now if I look again at the left-hand side, I've got t cubed times the derivative of y plus 3t squared times y itself, undifferentiated. And so if you think back to what we did on the previous problem, we can recognize that this left-hand side has the structure of a product rule. And it's important to note that the t cubed, the mu of t, had to be chosen perfectly. If we tried to multiply the entire equation by t squared, then this left-hand side would not have the perfect structure to be rewritten as a product rule. So somehow this t cubed, this mu of t, must be chosen very, very carefully so that this left-hand side turns into exactly what we need it to. Next, as we saw in the previous example, I'll integrate both sides with respect to t. Here I've gone ahead and just evaluated both of the integrals. On the left, we said that the integral with respect to t will cancel this derivative with respect to t. So I'll just be left with t cubed times y. And on the right-hand side, it was a relatively straightforward integral. If I'm just integrating t to the fourth plus t squared, I can integrate that directly. Next, my goal is to identify the solution, y, to isolate y in this equation. So I'll simply divide the entire equation by t cubed. Dividing by t cubed and simplifying gives me y equals t squared over 5 plus 1/3 plus c over t cubed. And this is my general solution. This is the solution to my differential equation. So to summarize this example, we once again started with a first-order linear differential equation in standard form. We multiplied by a given mu of t, in this case it was t cubed, and we saw that mu of t has to be chosen perfectly, because on the left-hand side, we want all of the ingredients to line up so that this left-hand side can be written as a product rule. That is, as the derivative with respect to t of, notice this is mu of t, so the left-hand side becomes a derivative with respect to t of mu of t times y. Once we've written it in that form, we can integrate both sides, do one simple step of algebra to isolate y, and that gives us our general solution. These two examples demonstrate the procedure that we'll use to solve first-order linear differential equations, but it still raises the question, where does mu of t come from? In both of these examples, we were provided with mu of t, and as I tried to emphasize in example 2, that mu of t has to be chosen perfectly so that this structure, this procedure works out. So how do we identify exactly the right mu of t in order to enable this procedure to work? That's what we'll look at next. In order to understand the process that's required to construct the perfect mu of t, we're going to imitate the procedure that we just implemented in the previous two examples, but we're going to do so with a general first-order linear ODE. So instead of having particular components or ingredients like a specific P of t or a specific G of t, we're going to try to reenact the process that we just implemented using this generic first-order linear ODE. This process is elaborate and kind of complicated, and so we're going to have to break it down into a few steps. Let's give it a shot. Before we get started, over here in the margin, I want us to think about like a structure of an equation that's going to show up in this derivation. So I want us to look at it by itself before we see it when it shows up in this derivation. So consider a situation where we have two functions, f of x and g of x. Suppose potentially neither of those is a known function, but suppose our goal is to try to solve an equation of this form for f of x. You'll notice that my function f is not only an unknown function, but its derivative, which would therefore also be unknown, is also involved in this equation. The presence of that derivative suggests that trying to integrate might be useful. If I were to impose an integral on the right-hand side, I would have the integral of g of x dx. And if g of x was known, I would be able to evaluate that. What if I tried to integrate the left-hand side? On the left-hand side, I don't simply have the integral of f of x, I have the integral of this quotient, where I have f prime in the numerator and f of x in the denominator. You may recognize this structure if you were to have an integral, for example, where you had some quantity or some expression in the denominator, and then that derivative in the numerator, that might suggest that you should do a u substitution, and then the integral would turn out to be an integral of natural log of f of x. That's exactly the property that we're going to utilize here. So on the left side, I'm implementing a u substitution. I haven't shown the details here, but I choose u to be f of x. du would then be f prime of x dx. All of the pieces line up so that the integral on the left does evaluate to natural log of f of x. On the right-hand side, I'm not going to simplify further because there may be specific function g of x whose integral I will try to evaluate, or I may want to leave this general if I'm trying to do a general generic derivation. As a final step to solve for f of x, I could exponentiate both sides of this equation, which would yield this expression for f of x. This is a little complicated because f of x is defined in terms of the integral of g of x, and that integral is in the exponent. But hopefully you follow these steps, and the main property of this derivation that's significant to notice is that when we have this structure, where I've got f prime of x over f of x, when I try to integrate that, that leads to natural log of f of x. That's one component of the derivation that we're going to try to do right now in order to find a general way of constructing mu of t. So I'm going to keep this off to the side, and when it comes time to use this in the derivation for mu of t, we'll have this as a reference. So let's get back to our original problem. We're trying to imitate the procedure that we used in the previous examples in order to understand how to construct mu of t. We start with general first order linear ODE y prime plus p of ty equals g of t. And if you look back at the previous examples, you'll see that our first step was to multiply by mu of t. Now in the previous examples, our goal was to solve for y. We were trying to find the solution to the differential equation, the unknown function y. In this particular derivation, our focus shifts, and we want to try to solve for mu of t because we're trying to understand a general method to be able to construct that mu of t. Looking back at the previous examples, you'll also recognize that in both cases, this left-hand side had all of the ingredients which enabled us to call this a product rule, or the result of implementing the product rule. In the previous examples, the mu of t had been chosen just right, so that when we multiplied through, this left-hand side became the result of a product rule. What we want to do in this derivation is to force that to always be true. So as you'll see, my next step will be to force the quantity on the left-hand side to be the result of the product rule, specifically the derivative of mu of t times y. Let's go ahead and set up that necessary equation. Here I've set up an equation where those two quantities are set equal. I can expand the right-hand side. I can copy the left-hand side unchanged. And then I notice there's a term in common on both sides. This mu of t y prime appears on both sides. So if I was to subtract that from both sides of this equation, that term would cancel out. Simplifying a little bit, I also notice that these y terms are in common. So if I was to divide both sides of the equation by that, those y terms would be eliminated. Let me take this expression and just modify it a little bit so that I isolate my mu's on one side and my p of t on the other. Here I've divided by mu of t, and then I actually switch the sides, so I put p of t on the right-hand side. This resulting equation is exactly the form of the fraction of the quotient that we worked through before we started this derivation. So do you see over here on the right we had f prime over f equals g. Here we have mu prime over mu equals p. So I'm going to use this derivation here that we did earlier on the right to be able to go ahead and, in this case here, we were solving for f. In this case, we have the exact same structure, and this will allow us to solve for mu of t. So here we have identified a formula that will construct the perfect mu of t given initial or starting ingredients, in this case in terms of p of t. This is a slightly complicated formula because, again, mu of t is defined in terms of the integral of p of t, and that integral is actually in the exponent. But this general derivation does not rely on any specific functions, p of t or g of t. Therefore, this general derivation should work for any first-order linear ODE. If I now return to my original differential equation, and if I can make the assumption that we forced here, if we can make the assumption that this left-hand side is in fact the result of the product rule, that is the result of the derivative with respect to t, mu of t times y, then let me see what happens to the rest of my differential equation. Building off the assumption that this left-hand side can be written in terms of this product rule, which it should because we now know how to construct mu of t in the perfect way so that the left-hand side really will be this product rule. Then, as we saw in the previous examples, to proceed with the solution of this differential equation, I just need to integrate both sides with respect to t. The integral will, of course, on the left, cancel out this derivative with respect to t. And on the right, we have introduced that integral. We're solving this in a general way, so we don't know how to evaluate this integral mu of t times g of t, but we trust that we can do that in a specific problem. Finally, to get my actual solution, y by itself, I just need to divide by mu of t. My work has gotten a little cramped here on the page, but if you look at this final step, this final equation, we have isolated y as a function of ingredients that we started with, g of t, or an ingredient that we constructed, mu of t, based on the other ingredient that we started with, p of t. So this is the general solution. And this procedure, since we haven't utilized any particular specific functions in this procedure, it should work for any mu of t, g of t, and p of t. Again, this is a little cramped here. I'd put a box around that and label that as my general solution, but I've sort of run out of space. Fortunately, as we scroll down the page a little bit, I have typed this up and provided a little summary. So theorem 1 in the middle of this page provides a summary of the procedure that we just went through. It says that if you've got a first order linear ODE, y prime plus p of ty equals g of t, then the general solution is given by that formula that we just derived. And then the question is how do we choose that mu of t such that that procedure works out? And as we saw above, that mu of t is given by this expression here. So this theorem provides a concise, direct way to solve any first-order linear ordinary differential equation. There's an important note that follows this theorem that I just want to clarify. As you saw, when we are creating mu of t, we need to evaluate an integral. Specifically, we're going to evaluate the integral p of t. The note here says that when we're deriving that integrating factor mu of t, you do not need to introduce a constant of integration. So when you are deriving mu of t, you do not need to introduce a constant of integration. But in the final integral, which yields the general solution, you do need to include a constant of integration. Can't forget to include it at that stage.